I was actually going to do a slide on this. I haven't got it done yet. That is actually a little cartoon of a tombstone with HID RIP on it, because really as of this year, pretty much all of your top flight LED companies are all at 2.2, 2.3, 2.4, even 2.5 micromoles a joule. They're 25 to 40% more efficient electrically than HPS. So it's really the kind of the death knell of HID for at least people that can't afford either one. I mean, obviously there are situations where you can't, but if you have the money for either one, the LEDs really do outperform them in pretty much every category, whether it be yield or efficiency, whatever you name it. They're superior at this point. I'm going to kind of blow through here real quickly some of the early parts, understanding HID lamps. A lot of people will hear about ceramic metal halide lamps. They'll try and portray them as something different than a metal halide lamp. There's really no difference in a ceramic metal halide lamp. The only change is they change this inner tube in here to ceramic, the same kind of glass that they have in the HID lamp. What that allowed them to do was put a lot more of the red halides, made the red halides more stable, so the lamp would preserve that red color a long time. If you remember, the old metal halides would always go green whenever the lamp would get old, and that's because that red halide is very reactive, number one, and number two, it actually can permeate through the glass. So the ceramic tube made the ceramic metal halide much more stable, color stable. It was originally developed for the film industry, but it got translated into the horticulture industry. So this shows you HID. A lot of your HID systems, you'll notice, have a dimmable knob on your ballast. The problem is HID, high pressure sodium, is why it's called high pressure sodium. The reason is the pressure of that lamp actually affects the spectrum of it. As you look at this is the lamp. This is from the original papers written by the guys who invented the HPS lamp back in 1953 or something, 57. And you'll notice this is at like 200 watts, 400 watts, 600 watts on a 600 watt lamp. You'll notice that almost all the power is right at the sodium band, which is this yellow band. As you increase the pressure, you'll notice that more of the energy keeps getting squashed into the sides, and interestingly, right around the sodium band, it starts to drop. So the problem with dimming an HPS lamp is that as you dim it, it goes this way. Okay, so if you dim your HPS lamp 20 or 30%, you may be getting 40 or 50% less photosynthetically active energy, because this area here is really the only efficient photosynthetic energy in the light. The green-yellow is about 40% less efficient. I'll get into that a little bit later. But that's why it's not a good idea to dim either metal halides or high-pressure sodiums, whereas LEDs can dim absolutely perfectly. There's no change to their efficiency. In fact, they get more efficient when you dim them, and the spectrum doesn't change at all. So again, as I mentioned, this is really the area where you're going to tie into the chlorophyll peaks. This area here is really somewhere in the range of around 40% less efficient in terms of actual photosynthetic output, the green-yellow region. All right, again, that's the double-ended lamps. The difference, what happened in double-ended lamps is basically they made the lamp a lot smaller. The arc path got shorter so that the stability of the arc path was better. They gained maybe 10%, 15% in the lamp design. But the biggest reason why double-ended lamps are so much more efficient now is actually fixture savings. The old fixtures were incredibly inefficient. They had glass lenses, a lot of them, most of them were air-cooled. The reflectors were not well designed. Now, Gavita literally, with this double-ended lamp, as the lamp gets smaller, and the smaller that arc path gets, the easier it is to get all the photons out of the fixture in one bounce. That's your goal in designing a reflective fixture, is to try and have every single photon that's going backwards, is not going out the front, come out of that fixture in one bounce. And by getting the lamp very small, the arc path very small, with a really highly well-designed fixture with no lens on it, you're able to do that. So Gavita's literally gotten those fixture efficiencies up to around 95%, where they used to be maybe 80 or 75%. So that's where believe it or not, that's the big advantage in these new double-ended lamps, was the fixture efficiencies were so dramatically higher than any of the stuff that you were seeing with the single-ended lamps. Same with the ceramic metal halide. Not only are the lamps a little more efficient, but the fixtures are dramatically more efficient than they used to be. So again, the whole idea of LEDs is to try and, fixture efficiency is trying to get that light out in one bounce. So this is a really rudimentary reflector. You can see where you might have to bounce 2 or 3 times to get out of there. One thing you want to remember when you're talking about HID lamps is if they rate 20,000 hours or 10,000 hours on the lamp, that's a half-life. That was designed back in the days when they were lighting warehouses with them. So that basically told you in 20,000 hours, half of the lamps will still be burning. It is absolutely not usable and not appropriate or worthwhile information in horticulture. That's why most people are replacing their HID lamps in anywhere from 6 months to a year. So with LED designs, basically you have a ceramic substrate on the bottom. This effectively is an insulator from the chip to protect, that insulates it from the board below the actual circuit board, and it also is the primary heat sink of that chip. Okay, and then you have the lens on here, and in your white LEDs, this lens will actually contain phosphors. So this would be a blue LED that would be irradiating those phosphors, and the phosphors would create white light. In discrete LEDs, that's just a clear lens that gives you your throw. So that can change. A normal LED is 180 degrees. It goes in all directions. More, it's almost a perfect mountain type curve. More in the middle, and then as it spreads out to the sides, it drops off, but it's 180 degree type spread. What this lens allows you to do is take that down to 120 degrees or 80 degrees or 90 degrees or whatever. All right. Okay. This is a funny article I read in Phys.org. Some universities' engineering department literally published that they got more energy out of an LED than they put in by running like microwatts through a 3-watt LED, and there was this whole, and they published this. I can just see the physics department pulling their hair out, screaming, "No, you didn't actually publish that, did you?" Because obviously it's impossible. It's ridiculous. But what it does tell you, and they've documented this numerous times, is LEDs efficiencies, when you run them really, really cool, if you keep that junction temperature really, really low, the efficiencies are remarkable. They can get upwards of 90% or better, where right now they're running around 30%. So the future of LEDs is really bright. I mean, it's almost unlimited how much, up to 100% efficiency. They're going to continue to get better and better and better and better. And it's mostly about this substrate. It's mostly about improving this heat conductivity of this substrate material. Now, the majority of your LEDs out there are plastic substrates. The industry is starting to make a move. Osram was the first one to go to a ceramic substrate. It doesn't conduct heat dramatically better than the plastic, but the material itself has a similar density and hardness and porosity to the chip, the silica chip itself. So you're able to make a much more dynamic, much stronger bond between the two. So the thermal conductivity is more consistent over a long period of time. And if you look at that's the fixtures. If you look at the Osram, this is published by Osram, the majority of your LEDs out there that have a plastic substrate are talking about 30% degradation over 50 to 60,000 hours. Now, granted, flowering, that's 18 years, right? It's a long time. But Osram with the ceramic substrate is literally talking about 90%, so 10% degradation over 100,000 hours. So really, the lifespan of these LEDs they're going to last a lot longer than you're going to want them, than you're going to be using them. You'll have to replace them probably long before they wear out, purely from efficiency gains. So that's the beauty of LEDs. They're extremely robust, extremely reliable. You can use them for 10 years and they won't change. You don't have to touch them. There's been a long-standing argument about passive versus active cooling in LEDs. And kind of the common sense feel about it is, well, why would you want fans? Fans are the #1 failure point. The fact is that whole mindset comes from these Chinese ballasts that always have a fan that's the first thing that fails. I don't know if you guys have had these Lumitech and these other ballasts, and it's always the fan that goes out because they use cheap fans because they want you to buy another one in a year. But the reality is that if you buy a high-quality server-grade fan, they last 50, 60,000 hours absolutely reliably. So fans really are not a chance. They're extremely inexpensive. So the overwhelming, I should say the dominant opinion in the industry is if you can use fans, go ahead and use them. It's better. You'll keep the chips cooler under a wider variety of environmental conditions than you will under passive cooled. The advantage of passive cooled, the only real major advantage is it's easier to make it waterproof. Obviously, if water and rain and everything's going to be splashing on it, you don't want a fan in there. They make them waterproof, but still, that's an environment that's not going to be super conducive to fans. So that's really the major advantage of passive cooled. Other than that, there really isn't one. Fan cooling is better, it's superior. But you know, you start getting your big lights like the Fluent Spiders, things like that. Obviously, passive cool is the only way you can do it when you do big strips like that. So it depends on the design and the application, obviously. So now in spectrum, we all understand kind of the basics of spectrum. This is sunlight. You'll notice there's a little bit of a peak in the blue. Most of that is due to the fact that not only do you have sunlight coming through with a fairly balanced spectrum, then the skylight is a very blue, so it gives you kind of a peak in the blue region. This is how the eyes see light. And this is important when you start talking about lumens or lux and how you rate light or how you measure light. This is how the eye sees light, with a big spike in the green region. Well, lux and lumens are based on the way they're adjusted to reflect how your eye would see that light, the visual brightness of that light, not the actual photons coming out of it. So this is how plants see light, okay? You've got your chlorophyll A and B peaks in both the red and the blue region. The green region, where the eye sees the light best, is very, very low absorbability. Now, it actually is utilized better. If you see the McCree curves, it's utilized better than this. But the reality is still the green-yellow region is about 40% less efficient than the red and blue regions, the peaks anyway, of the red and blue regions in terms of actual photosynthetic activity. So you can't use lumens or lux type rating on any lamp. You can't really try and compare them because they're based on how your eye sees it, not how the plant utilizes it, all right? And there's the beta carotene also shows, and this is the curve. I probably shouldn't bother with this. This is the actual how plants use light. Basically, the light strikes the plant, the water gets the hydrogen stripped out of it, releases the oxygen. That hydrogen and the carbon dioxide are bound together and it creates a sugar. Literally, every 10 photons, roughly 10 photons creates a carbohydrate. So bottom line is, the whole goal in cannabis is to try and get as many photons as that plant can possibly absorb and utilize efficiently in that period of time that you have, because every 10 photons is a carbohydrate. And it's just that simple. It's very straightforward. Now, like I was talking about lumens are designed for eye. The way the industry rates lighting for horticulture is with PAR. PAR is photosynthetically active radiation. That basically means that it's weighting all of the spectrums that are in the photosynthetic region, from deep blue all the way to not far red, but the very far end of red. All of those spectrum are all weighted evenly. So that's why even PAR readings are not actually a really accurate way to compare lights. Because, as I showed you before, that yellow-green region is 40% less efficient, but PAR rates it the same. So that's why if you see a light, an HPS light, which is 50% green, half the spectrum of an HPS light is in green. If you see a HPS light saying 1600 micromoles, and you see an LED light that has 10% green, that has 1600 micromoles, that LED light has substantially more actual photosynthetic activity in a plant because all that green light has been taken out. It's using only spectrums that the plant can utilize most efficiently. That's until recently, until this year. It's just this year that all of the LEDs are now electrically more efficient than HPS. Last year, the entire market was roughly electrically, meaning the micromoles per joule rating, the power in to photons out. They were about equal. The vast majority of the LEDs were all about 1.8. So all the savings they were getting, which was around 25 to 30% for the better companies like California Lightworks, we were getting routinely in tests 25 to 30% savings consistently, purely on this photosynthetic efficiency. Literally just because of shaving out all that green out of the light, we were able to get 25 to 30% more efficiency versus HPS. Now with the 20% to 25% electrical efficiency advantage. The efficiency gain is really around 45 to 50% almost now. So that's why when I say HID, RIP, I mean this year at 50% more efficient or 45% more efficient, it's pretty much, this is going to spell the end of HPS as a practical solution for horticulture as of this year going forward. And this is why, because when you add those two together, it's a dramatically more efficient system. So what they really need, and this system isn't in place yet, is an adjusted PAR, is a way of taking the PAR value. And some of your PAR meters, if you invest in the really expensive ones that have software in them, you can actually take the PAR measurement and run it through the McCree curve. You can actually run it through this absorption curve down here, the utilization curve rather, and it'll give you the actual PAR, the adjusted PAR, of what the actual photosynthetic activity in the plant's gonna be. So that's really the only way, absolutely accurate way to compare two lights. I see a lot of people walking around the show with PAR meters, comparing lights with PAR meters, and it gives you a rough idea, but it's really not accurate. This is really the only way to know for sure really how the lights compare, is by running them through this absorption curve here. Here's some of your other lighting sources. Now this is a really good comparison. It shows you exactly where HPS lines up on the absorption curve. This is the overall peak absorption curve, okay? Look where it lines up. The entire of HPS is all in a relatively low efficiency area. None of it. It literally has nothing up in the high peaks except for this little spike here. And different HPS have different spectrums, so this can change a little bit. And then the newer lamps are starting to run higher and higher pressures, so they're starting to squash a little more of this on both sides. You'll see some of them will be a little flatter if they're running a little higher pressure. But the majority of the energy still, especially this whole half over here, that's why I say 50% in the green yellow, this whole half over here is all right here. So that's where we were getting all our savings last year and the year before that. Literally was there. Now with the electrical, it's just way more. We're getting 40 to 45%. Again, this is the idea, don't dim HPS. Okay, now there's two kinds of LEDs out there. One camp I call the A Billion Years of Evolution Can't Be Wrong camp, which says, well, sunlight's white. Plants have been evolving for millions and millions of years under white light. It must be best. And that makes perfect logical sense, you know. The problem is the science doesn't agree with it. The science suggests we know exactly where the plants absorb. We have these peaks, and the plant absorbs much more efficiently at these exact chlorophyll A and B peaks. Now there are other pigments that can absorb light and can translate that light into energy. All of them have to go through the chloroplast. They require chlorophyll A to be around to do it. Like the carotenoid system, the red and yellows in your plants, that's the carotenoid system. That's underneath the chlorophyll. The carotenoid layer is actually beneath the chlorophyll layer. That's why the carotenoid layer is less efficient. The actual conversion to energy isn't that much less efficient than chlorophyll, but it's beneath, and the chlorophyll's green. So the very color the carotenoids absorb is reflected away by those chlorophyll, which is kind of the green-blue region. So the white LED camp, or the full spectrum camp, says that white light is best. You have your white LEDs that are basically a blue LED with white phosphors. They create, let me see if here it is. So this is a white LED kind of spectrum. This is kind of exaggerated, but usually they'll have a big blue spike because it's a blue LED driving that white cob or that white LED. Blue LED, and then you have this is the phosphors creating this big mound. And then most of the top shelf LEDs will have a red spike over here too. Like Fluence, you'll notice they'll have a red spike. That's with discrete red LEDs. So they'll have their white LEDs that does this kind of a curve, and then they'll have a red LED giving them a little spike on the end. So that's one camp. Or middle halide would be more of a flat spectrum, but it's pretty high in the blue. But in all of those white LEDs, you still have this a major 30 to 40% of the energy is all being produced in this region that's underutilized by the plant. Now, the LEDs that I call the discrete LED designs, like California Lightworks, like LumaGrow, They use a combination of red and blue LEDs, specifically at the chlorophyll peaks, and then a white LED in a lower power density, like 20% or 30% of the total power, to cover the rest. And I think there's a pretty easy argument to be made that if you're trying to look for the absolutely most efficient way to drive a plant, this approach is the best. It's the most efficient. We actually see it in side-by-side testing. And it's not dramatically more efficient than the white LEDs. We're seeing somewhere anywhere from 5 to 10% better efficiency in terms of true photosynthetic activity. We can run slightly less power than a white LED and get the same growth rates because of this, because we're not wasting a lot of energy on the green. Now there is one caveat on that though. Green bounces around. It bounces off the chlorophyll and it does absorb, and it can absorb through the bottom of the leaves and everything. So if you have a canopy that's really unruly, that's not pruned properly, that has a lot of shading happening in it, lights with more green will actually perform better. That green will perform better in those heavily shaded canopies than it will in a well-pruned canopy. So that's why when they talk about HPS having better penetration, that's kind of what I think they're meaning and they're seeing, is that if they've got a lot of shading in their canopy, the HPS will give them some good penetration in areas that are shaded, because that green light's going right through the leaves, or it's bouncing off of them and bouncing around in the canopy. Here's the problem. You talk to any master grower worth his salt, and he'll tell you pruning that plant is half your yield. Half the game is shaping that plant so that nothing but flowers see light. And how much labor it takes to get you to that point. That's really probably the single biggest thing you can do to increase your yield, is to maximize exclusively flower seeing light and nothing else. So while the green helps in those shaded canopies, it's a really bad way to run a grow, having a lot of shaded flowers in your canopy. So, but that's how they compare to each other. So, all right, now we're going to talk about spectrum a little bit. There's a very fanciful term called photomorphogenesis. It refers to the fact that plants, all class 3 plants, in fact, all class 3 and class 4 plants, when they absorb different frequencies, they can actually make them show different pheno expressions. So we've used it for years. For 20, 30 years now, people have been growing cannabis. They've been using metal halide in veg. They've been using HPS in flower. The reason is because metal halide is a blue dominant light. And blue light tends to favor vegetative growth. It tends to promote leaf production and root production. Red light tends to promote flower production, fruiting, and stem production. So, and that's obviously, it's a function of billions of years or millions of years of, spring to fall. The light and the sunlight is more blue in the early stages, in the high growth period, during the middle of the growth period. As it starts getting into the late fall, it gets more and more red dominant, and so that triggers the flowering responses on a lot of plants that flower based on red light. So because of this, we can actually use the spectrum to tell the plant what we want it to do with the photons it's absorbing. As opposed to having one fixed spectrum and just letting the plant do whatever it wants, if you put more red light on that flower, it will produce more flower and less leaf. If you put more blue on that plant while it's flowering, it'll produce more leaves in those flowers. So if you've ever compared an outdoor plant, like an outdoor cannabis plant, to an indoor one under HPS, you'll see that the HPS literally just has little fingertip leaves coming out of the flowers, right? You look at outdoor plants, the leaves are big leaves coming out of your flowers. And metal halide has longer leaves coming out of the flowers as well. The reason is because there's more blue during the peak flower cycle. So some of that energy that plant is absorbing is going into leaf production instead of flower production. Now, any of you that have done a scrog grow and have trimmed all the leaves off and had nothing but flowers, know you don't need sun leaves to grow flowers. They really don't. The little leaves, even those little finger leaves of HPS, are enough to flower successfully and really get dense flowers with cannabis once the flowering cycle happens. Those sun leaves are helpful during the first 2 weeks when the plant's growing really fast and really big. But they're really not necessary later. So the reality is you want to try and drive. So why have we been using this ratio forever? Using metal halide in veg, using HPS in flower. By using discrete LEDs with variable spectrum, you can actually change the ratios of the red and blue throughout the flower cycle. So what that allows you to do is, say for example, a typical ratio of red to blue for veg is about 60-40, 60% red, 40% blue. We almost always, virtually any grow light you look at is going to have more red than blue because red is photosynthetically more efficient. The blue takes more energy while still making the same carbohydrate, so it's more expensive to do blue. Okay, so any light you want to run more red than blue. But in veg, to get lots of leaf and get you that true veg metal halide style of vegetative growth, you might run something like 60-40 red to blue, okay? What we do with California Lightworks or with LumaGrow, with any of the discrete type LED systems, in pre-flower, which is those first 2 weeks, you can crank the power up and run 70-30. You're still running a lot of blue at 70-30, because HPS is like 95-5. 95% red. It's hardly any blue at all. So you run 70-30 the first 2 weeks, keeping your plant kind of compact. If you don't mind, you got lots of room, you run more red and less blue, you'll get a bigger, stretchier plant, but it'll be bigger. Okay? One thing you want to remember is that there's no magic formula, there's no magic spectrum that's the best. Doesn't exist. Anybody tells you they've got the magic formula, it just doesn't exist. There's dozens of different ratios that will do different things, depending on what you want to do with the plant. That's the beauty of leveraging spectrum, is that there's a different spectrum to get peak yield, to get maximum yield for top shelf flower. There's a different spectrum for maximum yield, pure yield. There's a different spectrum for extraction. You can literally, there's a different spectrum to keep the plants really compact if you're space challenged. So you can leverage this spectrum throughout the flower cycle to actually use that function, that photomorphogenesis, to get the plant to do what you want it to do. And that's a level of control you just will never get with a fixed spectrum light. There's no way to do it. Now, the yield advantages aren't dramatic. Like I said, we see between white and discrete spectrum in tests we've seen, it's somewhere in 5 to 10% range, advantages. But in terms of quality and flower structure, you can actually have some substantial differences if you're willing, but it's all a trade-off. If you want to get tons and tons of resin and super, super resinous, you're going to have to sacrifice a little flower mass. Your flowers will be a little smaller, but a lot harder and denser. You sacrifice, you run more blue, you get more resin terpene production at the end, but you get a little less flower production, actual flower material. You run more red, you get bigger flowers, but a little less resin because you've only got so much energy to work with. It's a trade-off. So people don't understand it. It's all a trade-off. There is no magic ideal. But with the discrete LED system, you have that flexibility to choose where you want that to go, where you want that energy to go. And as this industry matures, it's going to get more and more and more competitive. And quality is going to become, unless you're extracting, quality is going to become more and more and more important. With a discrete lighting system, you have the flexibility of being able to change that. You can sacrifice a little bit of yield to get denser and denser and higher quality if you need to. Those other guys can't. They got what they got. They'll try and do it with nutrients, and trust me, they aren't going to get very far with that. There's only so much you can do with nutrients. So this is, again, white LEDs. I generally don't even look at this thing, but I'm going to look at it. Okay, let's get into some other spectrums. UVB, this is an actual insert from the study done in 1987 by the University of Maryland at the University of Mississippi, the ultimate irony that all federal testing is done at University of Mississippi, go figure. But University of Maryland did a test with UVB from 0 to equatorial sun level UVB exposure, all the way through veg and flower. They actually did it all the way through the entire veg and flower process. At the end, they came to a baseline of 25. They said they were Mexican sativa plants. Seems pretty likely they were true sativas because that's a pretty high THC level for 1987. But their 0 UVB was 25%, 50% UVB was 28, 100% UVB of equatorial sun, which is roughly 500 micromoles or 500 microwatts per square centimeter, was 32%. So that was a 7% increase over 0 to 100%, or 33% more THC at equatorial sun. And it's linear. That's actually a linear function. So California Lightworks has a UVB lamp, for example, that we've designed, and we designed it specifically at 2 lamps over a 4x4 tray will give you effectively California, or 30th parallel UVB levels, which is roughly 350 microwatts a square centimeter. We chose that just because we know all the cannabis plants have evolved at least at that. We didn't want to go to, you can try equatorial sun if you want, but we're not sure that the indica plants are going to be able to tolerate that because they evolved at the 30th parallel. So 350 microwatts per square centimeter is a nice, safe amount of UVB for pretty much any plant, unless you're talking ruderalis. Again, if you're talking autoflowers, those are from Russia. So they're even a higher latitude, so they might tolerate less, we don't know. A lot of research to be done on this. But what you can pretty much assume from UVB is if you provide equatorial sun, you should be able to get somewhere in the neighborhood of 30+% increase in your THC levels. At California sun level UVB, you should be able to get 20 to 25% more UVB, or more THC. So if you've got 20% plant, that goes to 24%. It's a lot. Especially if you're, so I typically tell people, if you're in a market where your THC is aggressively measured, if you're in a market where your pounds, literally your price per pound is varied or is based on THC levels, any of those markets where THC is going to change your profitability or going to change your competitiveness, UVB really makes a lot of sense. But there's a layer of complexity. It's difficult. When you use your UVB in the room, you need to turn them off when you go in that room. You do not want to work under UVB because it's not the same as sun. Sunlight shuts your eye down automatically. It's super bright, so your pupil shuts right down. These lights are really dim when you look at them. So if you look at these lights without eye protection, you're getting 8 to 10 times as much UVB exposure from the lights potentially if you're within a couple feet of them. You walk in there. I used to walk in my room. I had UVB lamps in there, and I'd walk in there and forget about them, and they'd be 6 inches from my head. Literally, I'd be walking around like, oh crap, and I'd run back outside. Well, I've been standing, at 2 feet. If you're getting 300 micromoles at 2 feet, you're getting 1,200 micromoles at 6 inches, or 1,200 microwatts. So you really have to be careful using UVB. I strongly recommend it if it makes sense in your market, if it's going to make you more competitive. But you really got to be careful. Put it on its own circuit, control it separately. And the California Lightworks UVB lamp now comes with a little flashing LED that's going to drive you crazy if it's on. So if you're in there, it'll drive you nuts because it'll be flashing all the time, and you'll know that it's on. You can turn it off. So now let's get into application. Oh, one other thing I want to mention. Typically when you're comparing LEDs to HBS, you're just comparing pure energy savings. But if you can actually increase your canopy, for those of you that have power challenges, your panel just won't handle, you got plenty of space, but your panel's undersized, and you don't want to mess with that, you can pay for your lights, LEDs in a crop or two, a turn or two, because you can increase your canopy by 40% if you go to LEDs, if you're power challenged. You're not just counting on the energy savings. Now you're talking 40% more yield each round because you can run 40% more canopy on the same amount of power. So that's a really fast payback if that's your case, if you're power challenged. Much faster than just energy savings. Now, I'm going to start getting into, there's a really commonly misunderstood aspect about lighting. The key to lighting plants indoors, whether it be green, and this is true of greenhouses or indoors, is you want to try and get as close to true diffusion as possible. Diffusion means light coming from all directions. All right? Routinely, throughout the last 20 years, the common mindset was you put that light down close. Put the light down close because it gets more penetration, right? Inverse square law says the closer you are, the brighter the light is. Problem is, the inverse square law doesn't mean the light is brighter. It only means that as you get closer, it's illuminating a smaller area. As you raise the lights, all you're doing is expanding the area it's illuminating. Every photon still reaches the bottom. There's no losses by raising the lights up, unless it bounces off the walls. So, but when the advantage is when you raise the lights up, is now all of a sudden you start getting crossover. The lights start crossing over and hitting different parts of the plant that you would not see. If you look at a plant and you put the light down close, here's a perfect example. If you take a Christmas tree shaped plant, style plant, 4 foot tall with a 4 foot diameter base, okay? The circle that that base creates on the floor is 10 square feet. But the cone of that Christmas tree shaped plant, the outer cone it forms, is 70 square feet. That's how much more leaf area there is than the footprint on the floor. Well, the closer the light is to that plant, the more all the light can see is the footprint on the floor. When you get that light right down and there's one light straight over the top of the plant, all it's shining on is an area of leaf the size of the footprint on the floor. Everything else is shaded. As you raise the light up or make it bigger, because that effectively is the same thing, making the light big or raising it up and getting them to overlap does roughly the same thing, because it's getting the light coming from multiple directions. As you raise it up and get diffusion, now all of a sudden you're lighting more and higher percentage of that canopy evenly, because the lights are crossing over. This plant is here, now all of a sudden this fixture is shining on, that fixture is shining on, that one's shining, all these different fixtures, so the light's penetrating in. And what it does is it takes it from a planar lighting to a volumetric lighting. And remember, all of our lighting measurements are always in square centimeters. They're always in this planar measurement. But canopies aren't planar, they're volumetric. And as you raise those lights up and get more diffusion, you'll illuminate more square feet of actual leaf area in that plant. And as you do that, believe it or not, your power density can slowly drift up because you're using more of the plant. You're not overdriving those areas of the plant that are exposed while the shaded plant's part's not being used. Plants were designed with the sun to have the sun move, so it moves around. It's very intense in one place, but it constantly moves. Indoor grows, you don't have that advantage. So if you have shading happening in your plant, you're wasting that leaf absorption in those areas while overdriving the other areas. The only way to stop that is either to do like a scrog, where literally every square inch there's no shading anywhere. You've gone through all of the mechanical effort, the work to get the canopy perfectly manicured so that it all sees light. Or you raise those lights up, and most of your commercial grows, you don't have the time to do that. Most of the big commercial grows I see, they're not doing scrog grows because it's way too time consuming. So if you're down a 3 or 4 foot tall or 5 foot tall plant, as you raise those lights up, now you're illuminating more and more and more of the leaf area of that plant. You're turning it into a volumetric canopy. But your power density is going to, on any one leaf, is going to slowly drop because you're spreading it out over more area. So believe it or not, that allows you to raise your power density, your amount of power up. If you're running 800 micromoles right now on your grow, if you raise those lights up and get a really, really diffused light on that plant, you might be able to pump that up to 1,000 and use it, utilize it properly. And you will get higher density in the bottom of the plant, you'll get higher density throughout the plant, more even distribution and density throughout the plant by doing that. So it's strange, but it's just counterintuitive. I know everybody thinks down close is better, but it's not. Now think about this too. Here's another example. If you've got a 2 foot tall plant, and you put your lights 2 foot above the top of the plant, and the bottom branch is 2 feet below the top of the plant. So it's 2 foot to the top, and it's 4 foot to the bottom branch. Inverse square law says x to the top of the plant, 1/4 x to the bottom, right? Inverse square of the distance. Now, if you raise that light to 6 feet above the top of the plant, so it's 6 feet to the top of the plant, it's 8 feet to the bottom branch. Now you square that, to the top it's 36, you square it to the bottom branch, it's 64, it's half as much light. So purely just through the inverse square law, if you look at it from the inverse square law, as you raise the light up, yes, the intensity from that one light goes down because you're spreading the light over a bigger area. But you've got all the other lights overlapping, so the power density stays the same. Whatever you put power up there is what you get down here. But as you raise the lights up, any one light, the differential between the top and the bottom gets less and less and less as you raise the lights up. You start getting a narrower and narrower band, a band that's closer in terms of total light level. 5 minutes? Okay, let's go ahead and have some questions. Anybody have questions? Yeah?
I'm doing a nursery,
Mm-hmm.
so I'm really focused on
Here, so everybody can hear you.
Mm-hmm.
I'm doing a nursery in Southern Oregon. I'm really focused on rooting.
Mm-hmm.
I'm wondering if you had looked at any studies or have any information on optimum LED lights. So I'm definitely going to be using LEDs for rooting.
Well, from what I've been able to see, I haven't seen a lot. I've looked, and I've not seen any really specific data on spectrum affecting cloning, rooting and cloning. But I have seen some that suggest that blue light tends to enhance root production. Red light, the different ratio of red to far red, interestingly, has a similar effect that it does in the plants. Oh, by this is one thing I wanted to mention to you guys too before we go. Far red is what causes plants to stretch. It's not lighting level, okay? Plants don't stretch because they don't see enough light. They stretch because shade light has more far red, and the ratio of far red to red is what's going to cause that plant to stretch. And that's the other reason why they stretch in flower. Because the same mechanism, the ratio of far red to red, is the same mechanism that triggers the flower response. So you're getting a shade stretch response and a flower response at the same time.
I just wanted to clarify the question also. It's not just about spectrum. It's about actual light levels. So
very low. I know people that do cloning. The lighting requirements for clones are very low, actually. It's really the key to cloning is all about temperature and humidity, preserving a really consistent humidity level at the canopy and keeping your temperature at that canopy consistent and the root temperature. It's really all about that, and oxygen levels, obviously getting that oxygen. If you're using clone plugs, trying to get them to dry out to the optimum aeration first, because they always start out a little too damp and trying to get them to that perfect spot. But I'm not really an expert in that. That's not my field, so I wish I could help you more with that. But any other questions about lighting?
Yeah, I had a question. Earlier, somebody was talking about the phosphorus in the white LED and the degradation. And can you maybe speak on the possibility of spectral changes in the life of the LED in regards to the phosphorus? Yeah,
the phosphors do degrade. Typically, it's not terrible. They degrade kind of in the 60,000 to 80,000 hour type range is about where they really start to degrade, where you get a noticeable amount of degradation. Again, is it enough when everything is going up so rapidly? All of the decisions of talking about 20 years life and all of that, when the light's going to be 30% more efficient in another 2 or 3 years, are we really going to be still using them? You know what I mean? In 5 years? When they're 45% more efficient again, the next generation. So I think where the commercial lighting is going to go is you're going to see these things being cycled through every so often, just like computer. I don't know that. A lot of people may run them forever, but if you're going to be as competitive as this industry is, and it's going to continue to be more and more and more competitive, you're going to have to stay on the cutting edge. And the power utilization in lighting is one of your number one biggest costs. So you're going to have to stay on that curve and stay ahead of that curve in terms of efficiency if you want to be competitive. Greenhouse is a little less important because it's only half your lighting that you're doing with. And by the way, on greenhouse lighting, when you look at greenhouse lighting, the other beauty of LEDs in supplementing greenhouses is that because they're dimmable, now you're not just turning them on in the morning and turning them off and then turning them on in the afternoon and turning them off. With LEDs, you can dim them continuously. California Lightworks has a photosensor control that actually dims those lights up and down. Sun goes behind a cloud, boom, they come up. Sun goes down behind the cloud, they come back down again, automatically, all through the day. So you literally can get a greenhouse to have indoor quality lighting by using LEDs as a supplementary light in greenhouses.
All right, we've run out of time. Let's hear it for Eric Harrington. Thank you.